Hello everyone, welcome to our first lecture. Um, Obviously, in the pandemic times, we're going to be doing things very differently. As I'm sure you already know, we're doing recorded asynchronous lectures and interactive live discussion sections. So first I'm going to tell you a little bit about this structure that I've kind of already summarized, but we're going to go through the slides anyway. And then we'll walk you through the big questions. What is machine learning and what is this course all about? So let's get right to the good stuff, shall we? First off, I'm sure you get this told to you with every single course, but please read the syllabus. We've put a lot of energy into trying to make this the document, the one that has the legalese which binds us together on how things are going to work this quarter. So I do guarantee you that when somebody, or more to the point, when 30 somebodies ask questions that can be answered by the syllabus, they're going to get one answer emails or one word answers in email or on Piazza that say syllabus. So please do check into that. Now, in these pandemic times, things are going to be very different. We're going to have to give ourselves a lot of leeway. I am right now recording this for you late at night because of family reasons, and I know that a bunch of you may be in the wrong time zone or have to go to work or things like that. So we're all going to give each other a lot of slack. And more to the point, we all need to not just give each other slack, but we all need to do everything we can to try to make up for the problems that are going to inevitably occur. We're going to have to give each other slack, but we're also going to have to pick up the slack and help each other out to make this whole thing work. In general, I'm trying to be as light as I can on any kind of hard and fast rules. I'm pretty open to changing things if it turns out that it's clearly going to work better for most people. Given that we are all in this pandemic together, and a lot of us are stressed out and dealing with crazy crud that we normally would not have to, I know that lots of people may need help beyond the academic. Okay? Maybe things aren't going well for you in a personal way. Maybe things are, crushing your ability to get work done because of extra things that are become your responsibility. Just come talk to us. It's not just to seek out answers to academic problems, but maybe we can help you with other problems, or at the very least we can make the right kinds of allowances. So, but back on the academic topic, if you do have questions, almost guarantee somebody else has the same question. So please do seek out help, seek to ask questions in a public place like Piazza, where we can answer that question and lots of people can get the answer, or come seek us out in office hours if you think you're going to need a detailed, long working out of something. Okay? And of course, discussion sections where you're going to find your excellent TAs. So we have two very, very good TAs this quarter. Jihai and Aparna will be taking your discussion sections where things are going to be both working through homeworks that you're going to get, trying to clarify concepts in lecture, and we're going to try to draw out some discussions so that people can find the actual more subtle points that are hidden within some of these things that we're going to bring up in lecture and in the book. So you also have 3 instructional assistants who are going to help run especially things on Piazza and do some grading, Yingxi, Aniket, and Jining, and I think that we're going to make a really great team. In a day or so, I'll finally get some time to upload videos. Everybody here has recorded a little introduction video, and you can find out more about us and our research and our personal lives. And by the way, I've really enjoyed reading all of the introductions on Piazza so far. There's there's a there's a surprising number of you that need to learn that tacos are better than burritos. I'm sorry. So scheduling, we know it's not live on the lecture. You already know your discussion section, but um, we are going to be flexible about discussion sections. So if you're in a time zone where it's very difficult for you to make your assigned discussion section and a different one is better for you, please go right ahead and switch. If you are in California time zone, I'm going to ask that as much as possible you attend a discussion section that you're assigned to. That way we make sure that there's space for people to flip who really, really need to flip. By the way, on the time zone note, I think that almost all of your instructional assistants are in the Chinese time zone, so they're going to be particularly responsible for policing Piazza during normal business hours in Asia. And I think that may help out a number of our students as well. So everybody really wants to know, how is grading going to work? I'm going to continue a tradition in this course that there are going to be 2 options for you. And more to the point, they're not even options for you, they're options for the graders. Basically, in one weighting system, the final project is worth 20% of the grade, and in the other, it's worth only 10% of the final grade. And we're going to automatically apply whichever one of these 2 options is best given the points that you have earned during the quarter. So you don't even really need to do anything. It's just if you had a great final project and not so good midterm, then you're clearly going to end up on option 1. All right, there is an opportunity for bonus points, which is going to be for exceptional participation on Piazza, and also if you have gone above and beyond on the final project. So just quickly to note that Piazza, yes, please use it. Canvas is where all the slides are going to be and videos, and Gradescope is where you're going to turn in. There is an anonymous feedback form if at any point you need to help me make this class better, whether it's positive feedback too, that would be great. I certainly would appreciate that. So, final project. The final project, you're going to go ahead and do something in the style of an academic paper which benchmarks a bunch of different machine learning algorithms to try to find out which one does the best overall in a particular problem set. So this is a table from the paper which we're going to kind of steal data sets and format from. So on the columns there, going down the here you can see a bunch of different machine learning algorithms that are being tested. Support vector machines, artificial neural networks of different types, bagging and boosting. And along the columns here, you can see a bunch of different ways to measure how good the machine learning algorithm is at solving a given problem. And all the numbers reported are an average over many different data sets and different random trials of how good this algorithm performed at this measurement of goodness of performance. So what this paper did is it found patterns of when things are likely to be better or not so good. And you guys are going to do the same sort of thing, but with fewer of the algorithms and data sets than were done in this paper. So, again, course help. If you need help, please ask us whether it's academic or not. Come to office hours, communicate. Don't suffer in silence. And we do encourage that everybody in this class abide by the principles of community, and I really do think that we can all be a welcoming and inclusive place, no matter what your politics or anything going on with uh, your gender or race or anything. We are all human beings, and if a pandemic can teach us anything, it's that we have common enemies like viruses, and we should probably, do a little bit more kumbaya and a little less dividing each other. So, if you have concerns and you find that something has not gone well in terms of the level of respect you think you should be afforded, or if you've been harassed, please contact me or any of the instructional assistants or TAs. If you don't want to do that, you can go right to the special offices that have been set up to do this here at UCSD, and they are able to handle it in the right way for you for whatever has occurred. And finally, I'll close out the general section with this is a slide I usually put out for first year students, and I'm sure none of you are first years, but there are some very relevant points for somebody who's taking off in machine learning. I know a lot of you are really pushing hard to get into these kinds of programs if you're doing machine learning, computer science stuff, and I want to really emphasize that GPA is not what you're there for. It's a tool to get the thing you want. Okay. You have to take sanity breaks. You have to realize that sometimes learning is the more important thing than just scoring points. I also want to mention that right about now, many of you are probably sophomores and juniors. It is a good time to find some mentorship, right? If you can find people who are just getting ready to graduate or people who are entering the workforce right now that you become friends with, you can get lots of really great advice as you get to that threshold. Likewise, if you take electives that you like from professors that you think are interesting, you get a much better connection to those professors than in the large lecture halls that you may be used to from your first 2 years. And that is an opportunity to also get mentorship and find lots of new projects that you maybe could get involved with. And, machine learning, Silicon Valley style, is all about building, building projects, trying something new, putting it on GitHub, sharing it with the world. If nobody likes it, fine, move on to the next project. The machine learning world is very driven by accomplishments and projects. And I highly encourage anybody who's into this, into trying to enter into this world, to start building, creating, putting stuff out there. People care more about your track record of projects and contributions, and sometimes even failures, than they care about your academic credentials, at least in Silicon Valley land. So that's something that I want to encourage you to explore a bit more as you enter machine learning. Also, likewise, another Silicon Valley kind of lesson is set goals, but be ready to change them, right? When they start up a brand new company, they have a firm set of goals, but the people who have given them money to do it, they want to know that the people in charge of the company are willing to completely change those goals in order to make sure that they deliver an investment return. So if stuff isn't working, it's important to reevaluate periodically and figure out if it's time to try something new. And I think that's great life advice and great career advice. And finally, there is no such thing as a stupid question, but there are wrong ways of asking. Syllabus, right? So it's enough of that kind of stuff. Let's go ahead and think about machine learning, the reason we're actually here. I figured it was good to start off by asking Google, since Google itself is mostly the most sophisticated agglomeration of machine learning that is out there. So what does Google have to say? Well, machine learning is just regression, right? Or just statistics, or just if statements. all of these are truisms. They, you know, both that machine learning takes the form of these things and that you can generally append just to it. You can say, you know, all these really fancy things that people get excited about, buzzwords, in the end, they're really just a fairly simple concept or math with a really nice bit of implementation behind it. I'm going to say that you know, all of these are true, and we're going to explore each one of these elements through the course of the quarter. But I also want to say that in the end, you can find an overarching thing. You can actually just understand that machine learning in almost all its forms is actually just picking an appropriate model to understand your problem. And once you've got that model, you know how to minimize a particular function to make that model best fit the problem. So it is just really, in the end, finding an appropriate model form, and then that defines a mathematics that you have to find the minimum of, and that solves the problem. Well, if that sounds a little bit too kind of theoretical, let's bring it down to maybe a very particular understanding that we can come back to several times during the quarter. You know, the name of our textbook that we're using is, by the way, I should have had a slide on this. It's the Chris Bishop book, Pattern Recognition in Machine Learning. It is available free on the internet because Bishop has made it available for anybody to use, and that's a really good book. You can find your PDF out there, and you can also, if you do want to, buy a paper copy if it works better for you. But again, that digression aside, pattern recognition, right? Pattern recognition is something that we do as people. We're actually really, really good at it. And getting machines to do it is been the topic of more than 60 years of research. Before there were computers for us to do machine learning with, there was a lot of time that humans had. We spent thousands of years just, you know, being bored because we couldn't play our Nintendo Switch, okay? Because it had, you know, when you're 2,000 or so years ago, all you had to do for entertainment at night was to stare up at the sky. And people did, and they very quickly found patterns in the sky. Many of them were very easy to understand patterns, but some were much, much harder. The one that maybe caused people the most angst was that there are very few of these bright objects in the sky which don't move in a straight line. Almost all stars can just move across the night sky, and they'll be in the same place again on the next night and the next night. But some of them actually seem to wander around. Now, and even worse, they don't just wander around the rest of the stars, they don't move in easy to predict ways. So this is the planet Mars, and these are photos taken on successive nights of Mars's location against the backdrop of stars. And what looks really odd is that Mars doesn't just move across the sky, but at a certain point it appears to go backwards on its path and then move forwards again. So this is very troubling to ancient astronomers and stargazers. They had no idea what was going on, and they spent a lot of time trying to explain this over thousands of years. Until the Renaissance times, the standard model was that the Earth was the center of the Earth. Rewind. All right, it's late. The Earth was the center of the universe. And that implies, if you're going to see this kind of thing in the night sky, that tells you that everything is swinging around and around and around the Earth. And that must mean that if Mars is moving around the Earth like we seem to see it most of the year, come on back to me, focus. There we go. Come on. All right, we're going to put that down to pandemic learning. I apologize for the interruption. I'm going to try to recover this video by finding where my focus is. All right. Okay. So, so at any rate, the Ptolemaic model proposed something ridiculous, which is that Mars moves around and around the Earth, but it also spins around its own orbit, going like this back and forth. And that motion of it spinning around its own orbit is what enables the Ptolemaic model to accurately describe the retrograde motion of Mars in the night sky. And in the, all the way up from ancient to Renaissance times, people tried to understand this, and they built these ridiculous, very complicated armillary spheres to explain the motion of the planets and the stars against each other. This very complicated clockwork is meant to help understand that thing that we just put on the screen there. Well, along comes our hero Nicholas Copernicus in the Renaissance times, and he has an idea. What if indeed it is not the case that the Earth is the center of the universe, but rather that the sun is, and the Earth moves around the sun? In that case, here is the Earth moving around in its orbit, and here is Mars moving around in its orbit. So on night 1, the sight pattern of Earth to Mars puts it here. And on night 2, the sight pattern puts it over here. And 3, because Earth is on the inside orbit, and because it's on the inside orbit, its rotational velocity is a little higher than Mars, and it passes Mars up. And when it goes past Mars, it appears to move backwards in the sky briefly. So this radically different model has a very different way of explaining the same data. Aha! Maybe we start to understand a little bit about what this heck all this junk has to do with machine learning. Because in the end, what machine learning is it's taking a model and applying a function to try to make that model best fit the data. Now, if your model is crap, if it's a Ptolemaic model, if it's a geocentric model, a very overly complex model, it can still fit the data. It can accurately say and predict where Mars is going to be in the night sky. But the mechanism is wrong, and it is got implications to it that are not true, that kept breaking down beyond predicting Mars. So these overly complicated models are the wrong sort of model. The right sort of model is the heliocentric model, and I want you to think about this in machine learning terms. If your model doesn't fit the problem, you may get results, but they may not be good ones. And along those lines, just because what we're doing is pattern recognition, you also need to recognize that there are times that patterns can be found, but they don't exist. In the night sky, we keep drawing all these constellations. They don't actually exist. They're just from our point of view. And they have no meaning except for us to talk about the patterns. People are really, really good at seeing faces in rocks, right? We are excellent pattern machines, but it is not the case that there is a face in that rock. So again, not just do you need to be careful about finding the right model to fit your data and solve the problem you want to solve, but you've got to be careful that what you're trying to do is not finding patterns in what is actually noise. So we're going to chat a lot about this through the course of the quarter about how best to do this kind of thing. So let's see. So all that was a great, huge conceptual kind of leap, I realize, but we're going to try to bring it on down now to the learning of machine learning. We might ask ourselves, how can we humans learn to create machine learning systems, right? You're studying this whole thing. how can you learn all this quite deep topic in the best way that you can? So I think it always helps, like we just did, to start with intuition, with things you can kind of grasp a hold of as metaphors and apply them to a new system that is somewhat unfamiliar. And then we can add in something much more formal, some mathematics and statistics, to not just cement the intuition, but be able to find out things that wouldn't be apparent to us just using this kind of metaphor that we've been speaking in. In the end, math doesn't just formalize systems, it enables us to find new implications that we wouldn't have thought of in the past. And then finally, because machine learning systems are systems that actually get created in the real world, we need to talk about implementations, because in the end, your theory may be good, you may be working on the right problem, but if your software doesn't do what you think it does, there's no machine learning taking place. So I think that we can use these three things not just to create machine learning systems, but also to help you learn. So we're going to do the same sort of thing throughout the quarter that we just did. We're going to start with intuition, and as we're now going to go, we're going to get a little bit of math, and then we're going to add in at the end an implementation so that you can really get your hands around it, both to cement your understanding and to understand the ways in which the implementation itself changes the whole thing. So, in the end, machine learning exists at this crux of all these things, and we need to do them all well. To end up making a useful system, it's also important to realize that at the end, you may have a great model because you did all of those three things. You used your intuition, you developed formal mathematics, and you got good coding. But if you feed this great model that you created with those interlocking circles, those three elements, you feed it garbage, then, as we know from all the rest of the programming courses, garbage in is garbage out, and you're not going to get a useful system out of that. So in the end, we're going to add a fourth element, which is a little bit beyond the scope of this class, but I just want to mention it because it's really critical. How is your data? Is it measuring what you think it is? Is it useful for the task you actually want to accomplish? Okay, well, all that aside, it's maybe time to start with a little bit of basic math. I'm going to try one more time to get a lock here. Haha, that's where it is. All right, well, I'm glad you all got a chance to watch me dancing back and forth on my yoga ball here. And let's get back to actually lecturing. Break time is over. So, we're going to use x to denote input like we always do. And when you see a lowercase x, it's just a scalar. It's a single number, okay? But in machine learning, we are going to be using lots and lots of vectors and matrices. So most inputs to machine learning systems are not single numbers. It's not just height. It might be height and weight and eye color and 18 other variables that are the inputs to the system. So in that case, we're going to create a vector of elements to hold all those inputs. So we're going to use vectors as boldface, and we're going to have a subscript to them. So you can look at a vector as a set of elements inside a set of braces. And for the most part in machine learning, all of these elements are all going to be real numbers here. Okay? So it's going to be a row vector of m elements. So here's a particular example. Here's an input vector that's 22, 1, 10, 160, etc. So the entire data set, right? So that x, this bold-faced x of I is one input. We're going to be training a machine learning system on a set of inputs, a whole bunch of data samples. And we're going to talk about them as a set because this set with n samples has n vectors of size m in it. And it's a set because the order doesn't matter here, right? Occasionally, for mathematical reasons, when we're talking about implementations, we may turn that set into a matrix so we can do some linear algebra. All right, so prediction. Prediction is y. Inputs are x, outputs are y. You're used to this kind of thing. We're going to talk about it as a particular kind of output. We're going to say binary classification. Something is a 1 or a 0. It's a bird or it's not a bird. Okay? So we're going to write y equals -1 for something that's the negative class, not a bird. And we're going to write y equals +1 for something that's the positive class. We're going to say that is a bird. Okay? That's the output of our machine learning system is it a bird or is it not a bird? So the question that we're asking from our machine learning system is, given an input, this x vector, we want to predict the corresponding output y sub I. Is it a -1, not a bird, or a +1, a bird? Okay? The final part of this thing is the model itself, which is doing this predicting from the x. Something has got to stand between the x and the y and create the y. So we're generally going to be parameterizing a model. The model is going to be written as maybe a vector like this, w, which is going to have m elements that are going to be the same dimension as the input. Okay? We're also going to have a bias term. The bias term is a scalar, and essentially it's a way in which you can fit a line, right? So you're used to the idea of y is equal to mx plus b. Well, you can leave off the bias, the b, but then in that case, the intercept of the line always has to go right through the middle of through the origin, through 0, 0. Here, let me actually illustrate. So here is your x and y, and if you have some y is equal to mx, then you can define any line you want as long as it goes through the origin. But if you write y is equal to mx plus b plus a bias, then you can define your lines anywhere. Okay? So again, just to continue on with the ideas, data sample, we're going to have an inputs. We're going to have a transformation of those inputs, like mx plus b. And you can write that either as a vector notation or this way. There are equivalent ways to write this. And that is going to be that y is going to be this. Okay? So the dot there refers to a dot product between two vectors. So I should say this right here is the dot product of two vectors. Okay? And you could also write this a different way, and you may encounter this in the books that you look at, or as we go through the various lectures, we may end up showing the dot product instead this way or this way. So don't get too wrapped up in a particular notation. I'm going to try to keep things relatively consistent, but I know we're going to mess up at least once and use a wrong notation on something in a slide or something. All right. So the intense math of this lecture is over. Let's take a step back, okay? So what is the goal of your machine learning system? in the end, it may turn out that um, you have a completely different reason for using a machine learning system. If you're operating in a business and the business wants to predict demand for a particular product as you go through the year, what you're after is a prediction, right? You want your machine learning system to take the sales data and magically predict stuff so that they can get the right number of widgets out the door on the right time. Okay? We want to estimate why. It's a prediction task. Or to put it in the parlance of our astronomy stuff, we want to be able to predict where Mars is on the sky on a given date. Now, more scientific endeavors actually are usually more concerned with the model. We want to estimate W. We want to estimate, what is the nature of this model, and the parameters of that model might tell us things, right? So in my own research, where I'm looking at aging and seeing changes in gene transcription as people age, if I fit a regression on gene expression levels to age, and we find that a particular gene has a very strong slope with age. It seems like that gene decreases dramatically as somebody ages. That may be a clue that that gene is highly involved in the aging process, or at least affected by the aging process. So what we care about there is not so much, the prediction. We care about the model. What parts of the model say that what genes are actually really, really important in aging? Or in the case of our astronomy thing, what is the structure of the universe, right? We estimate the various parameters. What is the structure that reveals about the way the universe works? Okay. Let's hit a few more high points about the nature of machine learning. You almost certainly already have experience with understanding what is a supervised and an unsupervised learning algorithm. The real answer is that supervised learning takes place in the 118A course and unsupervised learning takes place in 118B. So, because realistically, it's kind of a false dichotomy. A lot of modern deep learning networks are neither fully supervised nor fully unsupervised. They do things like they take giant data sets from Wikipedia text, right? And they're not nobody goes out and says this word means X from the Wikipedia. What it does is it infers context from nearby words and then learns to link together clusters of words. And it does this by leaving out words in the nearby. So when you find you go and operate with one word from the article on machine learning, and you try to predict all the words that are in the sentence in the next 3 words of the sentence, the next 4 words of the sentence, right? And when you get one wrong, then you go and train the network to get closer to the right prediction. That's a kind of self-supervised sort of thing. It's not supervised in the sense that a person didn't go out and create a labeled data set, but it's got a set of data and it's trying to train itself in a supervised way. So that may not have been very clear, and I apologize for that, but trust me that there is really no hard and fast distinction between supervised and unsupervised learning. That in the end, what we're getting is really, in modern machine learning, is mixes of these two. But from the standpoint of the basic algorithms, the things that people first start learning on, it's relatively easy to make this distinction, and we are going to find it useful, okay? In supervised learning, there is a true target that we're trying to hit, and we're using those labels as a way to make the machine learning system do better. In unsupervised learning, there is no label. What there is that the data comes in and the model looks for regularities in the data. It has the nature of the model describes the kinds of regularities that it is capable of finding, okay? So you have to apply, again, the right model to find the regularities you care about, because it is absolutely true that in the case of this particular version here, that a different kind of model could just end up classifying on color, and it would just be reds versus yellows, okay? Or things with green leaves versus things without green leaves, and that might not be the distinction you want. So again, not to worry too much about unsupervised learning stuff, but there is no label, and in supervised there is. So another false dichotomy is regression versus classification. I think we're all probably used to the idea of what a regression is. You have some X value, like say how deep the sound is that an animal makes, and you have some Y value, the weight of the animal, and we try to predict the Y value from the X value. Turns out that the deep voice of the polar bear indicates its large weight, and the high pitch of the cricket indicates its lightweight, right? At least it's a good predictor that sound is predicting weight. Once again, here we have our y equals mx plus b. Now, classification is the idea that what you're predicting is just, is something a bird or is it not a bird in some arbitrary feature space that we've got here, okay? Now, in this setup, what you're seeing is that to find the positive cases, we're drawing a line here, a decision boundary. And everything on one side of it, we're going to call birds, positive cases. And everything on the other, we're going to call the negative cases. Once again, I will call your attention to that's a line. And the only difference between regression and classification in the sense of it's a line is just that in regression, what you care about is things moving together with the line, collinear with it, right? In classification, what you care about is perpendicular to the line. But other than that, it's the same math underneath. So a brand new topic is not just what is the algorithm, but how do you train it? So we have a bunch of labeled observations for doing this kind of supervised learning, right? Somebody has dropped on your desk a big old pile of observations for you to use. Now you need to figure out how best to make your algorithm work well. It turns out that what you don't want to do is use all your observations to train your algorithm, because then you're going to have no idea how good the algorithm actually is. Let's illustrate it this way. We want a training set and a test set. We want to take these observations and split them into two parts, okay? And we're going to use this part to train our algorithm, and this part, which has never been used to make the algorithm better, is going to be used to evaluate the algorithm on how good it is. So let's imagine here we have our birds and not birds, birds in blue, and how would you draw the line to separate out birds versus not birds in this training set? I'm going to stop for a second. I'm going to let you think about this. Imagine, where would you draw the line? Okay, put your finger on the screen. I know it feels dumb, but do it anyway. And let's draw the line, okay? I'm going to imagine a line something like this. Okay, that is my classifier. I have taken the training data, and in my massive machine learning brain, I have crunched the decision boundary that I think is most appropriate. So now we're going to draw, this test set, remember, comes from the same data set. It's really just a couple of samples that we held out and didn't do anything with. What do they look like? Oops. I think if we take this line here, which I'm going to have to freehand approximate roughly here, is not going to do a very good job on this test data. It's going to turn out that we have loads of errors on the test set. Why did that happen? Well, I mean, this is a data set with some noise corrupting it, or this is just that we only have a couple of examples and we happen to pick the wrong examples in this random division. This is truly the nature of what happens with machine learning. It's very easy for machine learning systems to actually do perfect on a training set. Most machine learning algorithms are more than powerful enough to make a zero error on a training set. But what actually measures how good the algorithm is really doing is its performance on samples it's never seen before that come from the same problem. That's where we learn about generalizability, about how good this algorithm is for generalizing to new data from the same problem, to new data of the same type. So we're always going to be in machine learning taking our data set we've been given and doing various things to it to get a better estimate of the algorithm's true performance. And a simple training test split like this is about the most basic version of what you can do that way. Okay, so let's take all that and apply it. So here is our version of machine learning is just if statements. Or if you want to think of it another way, machine learning is just drawing a line about what is a spam email and what is not a spam email. And we can draw that line in a space of words. How frequent are words in an email, right? So if your name is George and it's a real email, then that email is going to very frequently have your real name in it. And it's not going to have things like free or lots of crazy exclamation points or things that don't remove from list, okay? Spam, on the other hand, is going to use the word you instead of your name George, right? And it's frequently going to include things that may be dead giveaways. So all we have to do is we have to find the line we can draw, the threshold of how frequent we expect the word George to be in real email versus spam emails. Okay? And machine learning is just regression. It's just curve fitting. In this case, what we're doing is we're trying to find, again, that equation which best fits the data. Okay? Somebody's giving us a set of data points, and we're trying to fit the polynomial curve which best goes through these points. Now, I could fit a curve that looked a little bit more like this. That's terrible. Let's try again. That's like I don't know how many order polynomial, but it fits the data really, really well, right? It might even fit the training set perfectly. But if we assume that the underlying distribution is actually the one we see here, then if we draw new data points from the same problem again next week, then we might find brand new data points look like this, right? So now my 19th order polynomial that I drew here in blue is a terrible polynomial, and it's not doing well in generalizing to new data. So again, it's all fundamentally just going to be a matter of finding the right parameters for this equation to best fit a set of real valued data in this case. Okay. So what is the difference? If regression and classification really just share the same math, what is the difference between them? In regression, the ground truth is a continuous variable, one that you can actually compare two values of, right? You can say the polar bear is heavier than the frog. That makes sense to say, okay? But in contrast, in classification, ground truth labels are categorical. They're not real values. They're not numbers. They are something like it's a bird or it's not a bird. And it doesn't make any sense at all to say that a bird is less than not a bird. Okay, so that's really the main difference between the two things. Other than that, again, the underlying math is largely similar. Okay, so I'm just going to very briefly show you what unsupervised learning looks like. So unsupervised learning, again, is something where all you're doing is just extracting statistical regularity, say, or some other kind of mathematical regularity in the inputs themselves. There's no labels, nobody says what has to be X or Y, and maybe your algorithm decides that these things all belong together and these things all belong together, and those are the two classes of things in this data. The problem is that in clustering there is no ground truth at all. So, it just has to do with the samples we've been given and the model that you're applying, right? Those two things determine what gets clustered. Also, if you want to do this, you need to decide maybe how many groups there are and how to group and divide them. Okay? So the clustering problem is got a greater level of uncertainty. In fact, most of the clustering algorithms may not even give the exact same answer if you run it twice on the same data. They have a stochastic element. They have an element of randomness. Okay? So you may train it again on the exact same data and get a totally different result. So, the thing we're going to discuss next, and it's going to be next week, is features. Okay? When we say that there is an input vector x, right? Oops, sorry. When we say there's an input vector x, that x is composed of a bunch of features, right? What are those features? How are they given? Is there any difference between that and the raw data we've been given, the inputs? So it turns out that indeed that you can change the way a machine learning system functions, how good it functions, by taking the inputs and changing them into a different set of features. We'll discuss this again next week, and in the meantime, I hope that you have an excellent weekend and that all this stuff makes a kind of sense to you. I also hope that my focus is not going to come back. Oh, there we go. Now I can. Oh yes, pandemics are great. Learning how to do this stuff on the fly is the best. So I hope that your days are a lot less filled with errors than my autofocus. So in the meantime, I will see you again on Monday. Bye.